the way it is. Okay, so this is just a summary table of what we've talked about in terms of how we would work with solutions, right? Now, there's other ways that we can work with different types of concentrations of solutions, right? Because you can talk about ppms and ppms, parts per million, and then parts per billion, ppbs. ppbs and ppms, you know. So there's several ways of sitting there dealing with concentration. But these are the ones that, you know, that we want to kind of introduce to you. Like if you're getting into, when you get into your more focused areas, like if you're going into pest control, they often will talk about parts per billion, right? And parts per million, right? And in that regard, you're talking about, typically it's a mass, but you're basing it on a million or things to that extent. And they usually go into it a little more detail, but that's another form of concentrations that you're going to run into occasionally, and I'll probably add to this table. But right now, we're not going to do that. So we are on a timeline. So you guys are very familiar with this, right? So here, this is an example of, and often I use, this is what the text used in the book, but I use personally, C1 times B1 equals C2 times B2. Now, the reason why I use C1, V1, because concentration can be in any form, right? It doesn't necessarily have to be in molarity. And it doesn't necessarily have to be, it could be in molality, it can be anything, but when you do those dilutions, it's very similar to that concept, right? So you could do it in percent mass, or you can do it in percent, you know, in that regard. So you have some flexibility in terms of how you do it, right? But at the end of the day, it's your concentration times your volume, right? And then that's going to equal your concentration times your volume of the other. And if you're looking at the number of moles, right? So if you're looking at molarity, what are the units for molarity?
Moles over liter.
Moles over liter, right? Okay, and you're multiplying by the volume. Typically, we're going to measure our volume in liters, right? So you're just looking at moles at the end of the day, because liters are going to cancel out with each other. And that's the same thing on both sides. So you're saying the moles that I put in have to be the moles that I get out. Does that sound familiar to you guys? Are you there?
Yeah.
Yeah.
Okay, so moles that I put in have to be what I get out at the end of the day, right? What law is that, again?
Law of conservation.
The law of conservation, right? And so what we mean by that is that, so if I say that I have a molar concentration, a molarity of 1, and I'm multiplying by 1 liter, if I'm making 2 liters, I'm diluting my solution up to 2 liters. The concentration that I'm going to be, my C2, is going to be that concentration so that we end up with a mole. The quantity that you have in that solution isn't going to change, right? So if I have 50 moles in that solution, or if I have in this case, 1 mole in that solution, at the end of the day, it's still going to be 1 mole, but instead of being in 1 liter, it's going to be in 2 liters. So that quantity, the number of molecules that you have in there, right, is going to be the same. You guys get that, right? And so that's the reason why we can write that equivalency. That's how we can solve our C2, right? So then in this case, our C2 is going to be what?
That'd be 1 mole.
Is it going to be 1 mole? It's going to be 1 mole, yeah, that's correct. But what is going to be the concentration? Because C2 is concentration, right?
Half?
Half, that's right. So it's going to be half molar, right? Okay, so because that's what's going to give us 1 mole. So if we have half molar here and we multiply that by 2, how many moles are we going to have? So we're saying we have 0.5 moles per liter, which is molar. And we multiply that times 2 liters. How many moles are we going to have?
1.
Which is exactly what we started out with, right? 1 times 1 is going to be 1, right? Okay, so that's the reason why we can set up this dilution, and it works beautifully all the time, right? Because of that, okay? So all we're doing in that case is we're keeping the number of particles that we have in that solution the same, and we're just adding more liquid, right? So this is basically just showing you this, right? So let me clear my mess. What do you guys see in your screen? Do you see the full screen, full picture, or do you see my double screen?
The full picture.
Okay, so how many yellow dots do you have here?
5.
Okay, so the blue dots represent like water, right? So initially we have, 5 and, a total of, what is that? 17, right? 17 things of water. When we go after and we dilute the solution, then how many yellow things do we have?
5.
Still have 5.
We still have 5, right? And so quantity-wise, it's still the same, right? But concentration-wise, it's different. Do you understand?
Mm-hmm.
Okay. Piece of cake, right? Okay. So the process of diluting a solution is, okay, so we have whatever we want to dilute, right? So this is our stock solution. So in this case, this is 0.1 molar potassium chromate solution. And so then if we're going to dilute this, right? If we're going to dilute this down, so we're taking 100 mils of a 0.1 molar. So then what we would do, and usually you use a volumetric flask for this because it's a nice way of doing it. So you take that 100 mils, you pour it into a 1,000 ml flask, and now we're going to dilute this down to, I'm sorry, 1,000 mils. Yeah, actually it is 1,000 mils. 1 liter, so which is 1,000 mils, right? And so then we put the whole solution, that whole 100 in there, right? So if we take that whole 100, we're going to go ahead and pour that whole thing in there. We're going to rinse our bottle a few times to make sure that we're not losing anything, right? Because if we leave anything in the bottle, that means that we don't have that full 100 mils of that 0.1 liter solution. And so we go ahead and we put it in there, right? And then what we do is we fill this guy up to the 1,000 mark. And so the thing about a volumetric flask, and you guys have a volumetric flask, right? If I remember correctly in your kit.
Yeah.
So in the case of a volumetric flask, you actually have this nice, beautiful line, right? And that tells you the exact mark you need to come up to. If you go over that line, then you over diluted your solution. If you're below that line, your solution is too concentrated, right? And so it sets it up for exactly what you're planning to do, that volume you exactly plan to have. And so that's the reason why we typically use a volumetric flask. It's a quick way of making solutions at a certain concentration. But you always want to start off with your solute or your concentrated solution first, and then you want to bring it up to volume, right? You don't want to make the mistake that Christian and Israel made. Is Christian and Israel here? Since I'm talking noise about him. I guess not. Well, I know Christian's not here, but is Israel here to defend himself? I guess not. So I'll make fun of him tonight too. Okay, so this will be the correct way of making a solution. You never want to sit there and put 1,000 milliliters in here and then add everything in afterwards, because then is it going to be too dilute or is it going to be too concentrated? So if we already filled this up to 1,000 and then we add 100 to that, would that be too dilute or too concentrated?
Too concentrated, right?
So if I already have 1,000, say I put 1,000 mils of water in here. And then I add 100 mils of my solution.
Oh,
of my
sorry,
solution.
too diluted. Yeah, I thought it was the other way around. Sorry.
Yeah, too diluted. Yeah. So in that case, it would be too diluted, right? So, and we don't want that to happen. Okay. So we want to make sure that we're right at the correct concentration. So, piece of cake. Okay, and so we can also do that in math, right? So we know that our C1 is 0.100 molar. Our C2 we're going to calculate. So we're going to put a question mark there. We're going 100 mils. So how many liters are in 100 mils? So if I have 100 mils.
So 0.1.
Yeah.
Yeah. And then our V2, which is our diluted volume, is going to be, that should be liters, sorry. It's going to be 1 liter. So, how would I solve this? What is the equation?
The C1 times V1 equals C2 times V2.
And then we just solve for C2, right? So then we'll just have C1, V1 divided by V2. Oops, I forgot to put molar in there. Times. Running out of room. Being a bum here, put 0.00. Okay. And so our answer is going to be C2 Piece of cake? Yeah, no, maybe.
Maybe.
Yeah.
Anybody's gonna jump off bridges yet? No bridge jumping?
Close.
Okay, good. No bridge jumping allowed. Okay. Okay. So how many milliliters of a commercial hydrochloric acid, which is 11.6 molar, and that molar means moles per liter, molar, could be used to prepare a 5.50 liter of a 0.500 molar hydrochloric acid? So what do you think we're going to do?
Use our formula, the C1 times V1
Okay.
equals C2 times V2.
Okay, so we're going to use our formula. Okay.
So is C1 11.6 molar
Okay, so we'll go
or 0.500 molar?
where C1 So are we going to make it 11.6 or are we going to make it 5.5? I mean 0.5 molar.
0.5.
Okay. Okay. That
And then
means B1 is what?
Your 5.5 liters.
Wrong O. Liters. Okay. Okay, and then C2 is
11.6.
okay. Okay, so we want to solve our equation for
Me too.
B2. Okay, so it's around. Okay. Is that true? Did I screw up somewhere?
Zero 0.237.
Okay. So we plug in those numbers. Okay, so how many milliliters would that be? Zero 0.237 is liters, and it wants to be in milliliters. Oops.
237.
Okay. Oops.
Wouldn't the 1,000 liter be under, or would it be
Oops, sorry.
like?
Thank you for correcting me. Actually, it should be multiplied by milliliters, and then down below it should be liters. Good eye. I was just testing you.
Okay.
Okay. Piece of cake. Okay, you guys.
Dr. Henry,
Yes.
sorry. So when you know, like the 11.6 molar, would you say that that's always going to be like, because that's what we're looking for, right?
Yeah.
Like how many milliliters? Is it by default that we would put it in the C2V2 section?
Actually, it isn't. You could have put it in the C1, but then in that case, I mean your C1 V1 section, right? You could have done it that way since it's more concentrated. And typically that's what you normally do. But the beauty is that either way you put the equation, long as you're consistent about it, it'll be fine. So you know C1 goes with C2, C1 goes with V1 and C2 goes with V2. Long as you're consistent about it, the equation is always going to work out for you. You just don't want to mix up your volumes. You want your C1 to go with your V1 and your V2 to go with your C2. You understand?
Right.
Yeah. So it doesn't matter which way you do it, right? Most people like to do it like your C1 being your concentrated one, right? Which means 11.5 molar is more concentrated, you know, but you could have done it this way, as long as you're consistent about how you define those variables.
I see.
Does
Okay.
that answer your question?
It does. Thank you.
Yeah, so I won't, you know, spank you for, you know, mixing them up. But if I ask you about who's more concentrated, you know, and who's the dilute, then like if you defined your C D, which is C dilute, that's the reason why I don't like using the C dilute and the C concentrated, or, you know. Okay, questions, concerns, Ash? Credit? Okay, that means that if you guys, for every time that you guys don't answer, you owe me $1. Okay, so that's $15 I got so far. You guys see how this works? Okay. So I'm planning to make some money for the end of the semester. So far, I have made a dime. So we got to make something. Actually, I lost a bet. Okay, so here is, we go back to that whole thing with stoichiometry. So, you know, you can use the same thing for stoichiometry. So you can use molarity to sit there and do your stoichiometry metrics as well too, right? Because it deals with quantity. Although it's quantity per liter, but you're still dealing with quantity. If you're doing your reactions are happening in that liquid, right? In that medium, okay? So you can still do those conversions that you would normally do, right? So you can convert your quantity of a given species to number of particles, right? And then you could change that into number of moles. And then you can use stoichiometric measurements to figure out your moles of given to moles that you want of something else. Let me erase this so you guys can actually see what I'm talking about. All right? So this basically tells you, hey, guess what? You could sit there and use molarity and volumes of solution to do exactly the same thing, right? Because we know that if you have the concentration and the volume, or the volumes per mole, or you have your molarity times your volume, that's going to give you a number of moles, right? So if you use your volume and your concentration of your reactants, you can figure out the products, the moles of your products that you're going to be producing, right? And then if you have the volume of that, you can figure out the molarity again. You guys see that? You see this path here? So look at this. This is incredible, right? You've learned at this point, this is what you've learned. You've learned this, talked about energy, right? You've learned this. You've learned this. We're saving that for last. That's going to be our closer, you know? You've learned all of this. And then, of course, you've learned how to go back to that. That's what you've done. Are you feeling accomplished? Okay, that is $15. Hey, pay up. Let me give you my email account to pay me, okay? Venmo. You guys all have Venmo?
We were all on
No.
mute. We said
Well,
yes.
stop doing the mute. I can't hear you if you're on mute, right? I want to hear you.
I don't have $15.
Well, that's all right.
I
All
have
you
the
have to do
best
is-
I can give you is a Starbucks gift card for my birthday.
See, that'll work for me too.
You're gonna take his birthday gift.
I don't care. He should talk. We'll teach you. You know, talk
I'm
or pay
so
up.
sorry for not talking. I'm listening to you about owing you money.
But but it's a give and take. There has to be some give here too, right?
So
What
we
if
give
you
you
don't
money
have
in return
something
for an
to
A.
give?
No, you're not giving me money for returning an A. You're giving me money because you didn't do what you didn't hold up your end of the bargain. So you're paying for it, right? So I have to earn money some way. Okay, you guys ready? Next part?
Yeah.
Now let's sit there and apply this, right? So you already know how to do this, but the first thing that you want to remember is you want to change your molarity to moles. That is going to be your very first step, you know? And there's going to be a little shortcuts and stuff like that. We're going to avoid the shortcuts because I want you to suffer a little bit first, and then we'll talk about the shortcuts. Okay?
Yes.
Okay, good. And it's not really because I want you to suffer. I want you to see it, and then you can see how the shortcuts work. Okay. Maybe a little bit of torture. I don't know. Okay. Calculate the volumes in milliliters of 0.842 molar of sodium hydroxide required to precipitate as copper 2 hydroxide. All of the copper ions in 30 mils, 30.0 mils of 0.635 molar copper 2 sulfate. Calculate the volume in milliliters. Okay, so calculate the volume in milliliters of a 0.842 molar sodium hydroxide required to precipitate as copper 2 hydroxide. All of the copper ion in 30.0 milliliters of 0.35 copper 2 sulfate. Okay, so what am I going to do?
Is it going to be the C2V2 thing again?
No, not quite. We got to start a little way. Well, we have to start. That's going to be important, but hold that thought. Keep that up there. But the very first thing you do in a situation where you have a reaction is going to do what? Number one, first thing we should always do.
Write out your equation.
Write out my equation. So what is going to be my equation?
Sodium hydroxide, so NaOH. And then
And we know it's aqueous because it's a solution, right?
Oh yeah, aqueous. Yeah. Copper hydroxide, so that'd be Cu. Oh no.
Now think about it. So you have sodium hydroxide. So do you think you're going to be reacting with copper hydroxide? Because then are you really going to exchange hydroxide for a hydroxide?
Oh no.
That's kind of like divorcing your husband and then remarrying your husband right after. So what do you think is going to be the other reactant?
The
Copper sulfate.
copper.
That's right. And what is the chemical formula for copper sulfate? Of course, you told me the Cu. That's why I started it.
SO.
Sulfate SO4, right?
That's correct. So it's copper 2 sulfate. So is that right? Right number of coppers?
Yes.
Okay. Okay. So now we know that this is what type of reaction?
Double.
A double replacement reaction. So then I know my products are going to be
NaSO4.
Copper hydroxide.
NaSO4. Is that the right number of NAs? Na2. Okay. And we know that anything that's in that first group, in group 1, is going to be, oops, AQ. That's a Q. It's not a G. I don't know what I was thinking. Plus, you said copper. Someone said it earlier. Copper hydroxide. So it's Cu what?
8. 2.
Cu what?
Is it
OH?
CuO8?
CuO8?
H.
OH. Okay.
2.
Okay. All in parentheses, both of them, or just the H and 2?
The OH.
Okay. And is that solid, liquid, or gas, or aqueous?
Solid.
Okay. Okay. Is it balanced?
No.
Okay. What do I need to do to balance?
Put a 2 in front of NaOH.
Okay. Balanced now?
Mhm.
Okay. Okay. So now that we have a balanced equation, right? So you're right. We are going to sit there because we know that we can sit there and say moles is going to be equal to C1V1, right? Is that true? Our number of moles, or we can say N, which is what we normally use for number of moles. Well, maybe I should do that to make it difficult. So N, meaning the number of moles, is equal to C1V1, right? So if we multiply volume times moles over liters, what are we going to be left with? Are you there?
Yeah.
So I'm saying N equals moles. So we know that C is our concentration. In molarity. And V is volume. Okay, so it says calculate the volume in milliliters of a 0.842 molar sodium hydroxide required to precipitate as copper to hydroxide all of the copper ions in 30.0 milliliters of 0.635 molar copper to sulfate. So can I figure out how many copper ions are in 30.0 milliliters of 0.635 molar copper to sulfate?
Yes.
Yes, right? Because I know how to calculate the number of moles, right? Because if I just multiply the concentration times the volume, doesn't that give me my number of moles?
Yeah.
Yes.
Yes. Okay, so I'm glad you guys are working with me here. Okay, so let's start off with that. So let's start off with our given. So let's start off with this guy, right? That's going to be our givens here. We have a couple of givens here. So can I slide this over? I'm going to slide this over so you guys, we don't want to erase it yet because I want you to remember it. I'm going to slide it. Oops. Let's do this. Number of moles. Concentration and volume. Okay. Okay, so how do I change this into liters? Isn't our concentrators, isn't our concentration just moles over liters?
Yes.
Okay, so how would I do that?
1 liter on top and then 1,000 milliliters on the bottom.
Okay, 1 liter on top, 1,000 mils on the bottom. Let's see. Okay. And then our molarity is going to kind of serve as an equivalency, right? So, although we have to take the units into consideration, sort of. Okay, so what is 0.3 0.365 molar. How would I write that in terms of just putting it over moles over liters? How would I write that into moles over liters? So 0.635. Because molarity means, what are the units for molarity? What does it really mean for us?
Moles over liters.
Moles over liters, right? So that means on top I have how many moles, and on the bottom how many liters?
You have 1 liter on the bottom. And
Okay.
then the 635 is the moles.
Okay. So then I can put my 1 liter here. And then I can put my 635 or 0.635. Moles on top. Okay. So then if I want, I'm looking for what am I looking for at the end of the day?
The volume in
Okay,
milliliters of 0.8
Of 0.8 of what? 0.842 of what?
to molarity of sodium hydroxide.
So at the end of the day, I want milliliters Can you guys see that? Of NaOH.
Yeah.
Okay, so it says here all ions. Okay, so required to precipitate all of the copper ions. So what is the relationship between the copper 2 sulfate ions? So copper 2 sulfate. What is the molar ratio? How many moles? If I have 1 mole of copper sulfate, how many moles of copper 2 ions do I have? For every 1 mole of CuSO4, how many moles of Cu plus do I have? 2 plus, sorry.
1.
That's right, 1, because the subscript here is just 1. Okay, so that kind of works out to our favor. Okay, so then for every 1 mole of copper 2 sulfate, or 1 mole of copper sulfate, how many sodium hydroxides do I need to balance out this particular ion? How many of these do we have to this guy?
2 to 1.
Okay, so for every 1 mole of Cu, you have 2 moles So literally I could have just kept it the same right there without having to make that difference. And I'll show you why it may be different. Okay. Okay, so then that's going to give me my moles of sodium hydroxide. We have room here. So what do I need to do next? How do I get from moles to milliliters or to a volume?
Do we put the moles over liters again?
Moles over liters. So where are we going to get that from?
Would that be the 0.842?
Okay. So 0.84 moles over 1 liter. And that's NaOH. Okay. Oops. Okay, and then how do I change that to milliliters?
Liter on the bottom. And 1,000 milliliters on top.
Okay. Okay, so let's make sure, let's do some crossing out. Since these problems are getting like super long here, right? So milliliter, milliliter, liter, liter, mole, 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 moles, moles, liters, liters. Does that all look right so far?
Yeah.
Yeah.
Gonna go ahead and cross out this 1,000 here, and that 1,000 up here. So we can get rid of all these ones. So that one here, that one here, that one here, that one here, that one here. Okay, so I just have to worry about these numbers here. You circle them in hot purple or pink. So 30 and 2 and divide it by this number here. Okay, so
45.249.
so you said 45 point.
Or 25.
So that's going to equal, put my equal signs right here, set 45 and 3/6. So if it's 0.29, then it'll be what?
0.3.
So are we not multiplying the 1,000 on top as well?
Well, we're canceling out that 1,000 right here, right? So there's 1,000 at the bottom here, and there's 1,000
okay.
up top.
Okay.
Piece of cake?
Yeah.
Okay, questions, concerns, cash. Actually, it should be, maybe, because you said 45.249. So then it should be 45.2.
Oh, yeah.
Yeah.
Oops.
So that's why when we've talked about dimensional analysis, that's why it's essential for us to sit there and follow all of the dimensions, right? To sit there and make sure that we cancel everything out, because it starts to get very complicated because we're talking about tons of different equivalencies. We're putting them all together. You guys see that?
Yeah.
But you should ask me, well, can I do them separately? Can I just find a number of moles that I'm working with and then do that for the next equation? And then, yeah, you could do them separately. Or did I just read your mind or what? Any other questions? Or should I come up with more questions myself?
No.
Okay, great. Let's move on. Ready for the next one?
Yes.
Okay. Okay, clear. Okay. So titration. Titration is basically a way of finding equivalencies. So what do I mean? The equivalent point, or the point where you actually neutralize or equal the amount of one solution to the other solution to get a complete reaction. Does that make sense?
Kinda.
Okay. So to do titrations, right, we use what we call a Buret. And we often will use an indicator or a pH meter, right? Because often it's an acid-base type of reaction. And so an indicator will actually change colors to let us know when the solution has reached the volume that we want it to reach, so that it's equal in terms of the number of moles to sit there and balance out the equation and give us that complete reaction. Okay, let me show you what I mean. So this is a Buret. You've been introduced. You've been served. Okay, what do you think that means?
You've been served, serving you papers.
What was that? You've been
I just
served.
heard
In other words, you know what a Buret
Need
is, right?
some
So now it's fair game on the exam. That's what I mean. Okay, so this is our beaker. This here is our chemical stand, or it's just typically called a stand, right? So, and these are just your Buret clamps. Okay, so Buret clamps, chemical stand, Buret, and beaker. So this, I'm not beaker, I'm sorry, flask. This here is an Erlenmeyer flask. Erlenmeyer flask, okay? Buret, Erlenmeyer flask, chemical stand, Buret clamp. Okay, all fair game. This here is called your stopcock. Stop giggling, I see it in your faces. Okay, so the stopcock we use to control the volume that we're putting in. And the way that you would read a Buret is, normally you fill up the Buret to the very top. So at the very top, there is a 0 marker, and then it goes all the way down to 50, right? So then you keep track of how much solution you're adding. So you use your stopcock to sit there and add the solution until your indicator starts changing color. So that's what you're seeing happening here. Initially it's closed, we have it all the way filled up. Then we start dropping down our solutions that we're going to be reacting with each other. As soon as we get to that point, and again, it's usually an acid and base. And so usually you go from a situation where you have your indicator in your solution. You'll add enough so that you get an equal volume for the reaction, or you reach a pH that's neutral, right? Because an acid is acidic, so it's going to be pH less than 7. And a base is typically basic, which is a pH greater than 7. And when your acid and your base balance out, and this is for strong acids, we're not going to talk about weak acids right now. When an acid and a strong base balance out, you get water and salt, right? Which is basically neutral. And we know that pH of water is going to be 7. So we have indicators that will allow us to sit there and get to a certain pH. So we have what we call the universal indicator. Okay, can you guys see my screen?
Yeah.
Yeah.
You see so this here is basically a scale, color scale for the universal indicator. So, or at least this particular pH scale is your neutral would be 7. So this is what your distilled water is at. Anything that's more basic is going to be up here. It's going to be greater than 7, right? So, example, ammonia is a base. It's considered a base, where your stomach acids, your citric acids, you know, different fruit juices and stuff like that, all of those are going to be acidic. Okay, so if it's below 7, it's an acid. If it's above 7, it's a base. If it's at 7, it's neutral. So distilled water is neutral, right? Our tap water, depending on where you're at, may be slightly acidic or slightly basic. Okay. Questions, concerns, Cash? You guys understand that? So what happens is that our base, right, or we'd have that base in that solution. Pull up my screen again. So we would have our base in the solution, or we'd have our acid here, one or the other. So either our base is in the solution, and then our acid will be up top. And then so we would be titrating in our acid until it reaches a neutral concentration, or a point where we want that color change to occur. So this here, the color change is a result of the indicator that's been added to the solution. So that's the reason why it's going to change color. You guys get that?
So
Yeah.
the main point for this is that you use this to find out how much to add to make it neutral?
That is correct. So you can have an unknown. Let's say we have an unknown amount of our base, right? We don't know the concentration of our base. Some idiot made a solution and they screwed up and they didn't write down the numbers. That's typically what happens. So rather than having to remake the solution entirely, what you can do is take a sample of that solution that they made, put it in a flask, and then use an acid that you know the concentration of, and then you just titrate in that acid. So by doing that titration, you were able to sit there and determine how much or the concentration of that particular base, because you know that, let's say we're working with hydrochloric acid and sodium hydroxide. We know that the chemical equation for that, it's going to be a 1-to-1 ratio, right? Molar concentration.
Mm-hmm.
And that's going to just yield H2O plus NaCl. Okay? Questions? No questions? Excellent. Okay.
No questions.
No questions. Good. So what we'll do is that once you have the number of moles, like you have the same number of moles of of hydrochloric acid and the same number of moles, not molarity, but moles of sodium hydroxide, it's going to change. In this case, it would be a blue color, right? If we had used that indicator that we had that scale for, right? So let's see if I can show you again. This scale, right? So it would be blue when it neutralizes. So it would change from let's say a pink color to a blue color. Okay. You guys see that? If we had used this scale. Now, there are various indicators. There's tons of different indicators out there, right? Well, I'm saying right as if you know. But there are tons of different indicators. One, like I said, is called the universal indicator. It changes multiple colors. Some of them are only, they'll be clear under certain points, and then they'll change a color at a different pH, right? So the one here that they're probably using is the naphthalene, I believe it's called. And it basically, when it gets to a certain pH, it turns purple. And then it'll stay purple at all pHs above a certain point into a certain range. And then it may change another color, okay? Or pinkish purple. Okay, questions, concerns, Cash? Okay, perfect. So we basically will, yeah, go ahead.
Please, can you please throw more light on the scale again?
Can I turn more lights?
Yeah, like try and, yeah, on the scale.
Oh, you want to see the scale again?
Yeah, like just try and explain the scale one more time.
Oh, okay. Yes. So this here, the color scale is, so there are certain indicators, right? One is called the universal indicator. So the universal indicator actually is a combination of a whole bunch of indicators that are added together, right? And so when the pH is 1, right, the color of this indicator here, this is like a universal indicator. There's a couple of different ones. This indicator would be red, right? So the solution is going to be a red color. Okay. As we increase the pH of our scale, as it gets to neutral, which would be where we have water, right? So when we got a balanced equation, if we're using this chemical equation here, if these guys are completely balanced in terms of the number of moles, right? They're equal to each other, then you're going to have this reaction. If we have more of the acid, then the solution as a whole is going to be more acidic. If we have more of the base, the solution is going to be more basic, right? So if we're putting, let me show you. If I'm putting acid into this, so I'm using Buret and I'm putting acid in here. And this is my base, right? This is my base that's of unknown concentration. So what we'll do is, this base is going to have a color that's going to be associated with it. So since, let's say we're going to use our color, this is purple, purplish pink, right? Right now, that's the color that's going to be associated with it before we start adding the acid. So if it's purple and pink, purplish pink, where's that going to be at? Looking at our pH scale, what pH would it be?
Purple and pink, or just
let's say purple. What color does this match?
Pink.
Okay, so where would this match on this scale? Does it look like down here?
No.
Okay, where does it look like?
Is it, I don't know. I don't get what you're saying.
So the color, this color that I'm drawing on the board right now, what color is that?
Pink.
Okay, now on this color scale, which region does it match in? Does it match like 13? Does it match 12? Does it match 10? Does it match 8?
It matches with 12 or 11.
Okay, So it matches somewhere between, you say 12 and 11.
Yeah.
Okay. So does that look about right? I don't know. That looks more like this up here to me. Maybe I'm colorblind.
Yeah.
Which one does it look more like?
More
Somewhere up here. So would you say it's a base or would you say it's an acid?
is a base.
It would be a base, right?
Yeah.
Okay, so that means this is a base. Now,
Okay.
as we start adding more and more acid, the pH is going to start to drop, right?
Okay.
So then, if I have a color like, this is really hard. Say we have a color like this. Where would you say that one is at, roughly?
In terms of the number or either
The
base
number.
or acid? Huh?
The number,
8?
okay? So it'll be between, would you say 8? Between 8 or 7?
7 and 8.
7 and 8. Okay, so somewhere in here, right? So you'd say it's somewhere in here. So then you would say that the pH is somewhere between 7 and 8, right?
Okay.
Okay, so now if I have a color like this, let's say my solution now is, my eraser. My solution is this color. Okay, that's my solution. So if my solution is like that, where would you say that is?
If it's between 7 and 6,
Okay, it would be somewhere between 7 and 6. So is that acidic or is that basic?
acid?
It would be an acid, so it would be acidic. That's right. So that's how you would use that scale. So the solutions are going to change color as a result of the pH that they're at. And then that's how you would determine what the pH is. And so if you were trying to neutralize it, that's the term when you make it even to each other, right? When your number of moles are equal to each other, then in the case of a strong acid and a strong base, your neutralizing is going to try to be at 7. So it's going to be right at that 7 mark. So it's going to be more of that blue color. You see that blue color right there. Do you understand?
Yeah, thank you.
Okay. Everyone else, do you guys understand?
Dr. Henry,
Yes.
Yes.
I have a question.
Okay.
So in our kits, we got like a IKI indicator. Is that kind of similar or is that something different?
Yeah, that is kind of similar. Yes. So, but the IKI indicator, that's used to indicate starch, right?
Okay.
So we use to determine if starch is present or not. But yeah, it is very similar. Indicators can be specific to like a particular compound or a particular chemical, or they can just be like, these are just called pH indicators, right? So they're just there to determine your pH.
Okay. That makes
Okay.
sense.
But that's a good point. Good job. That's a star. And you're asking, what do you get from a star? I just talk good about you instead of talking bad about you. That's all.
Aw, I wanted chocolate.
You want a chocolate? I would love to give you chocolate. I have plenty to give too. And I need to give it because I keep eating it. Okay. So let's see if we can go a little bit further. Oops, wrong way. Okay. So often we will use the term, what we call is standardization solutions. So standardization is just basically we determine a known concentrations that we actually know, and we just confirm our titration, right? And so we're using it to standardize all the solutions that we're using, okay? And so those are things that we know. And then after you do your standardization, you make sure that your system is working, all your concentration is right. Then what you do is you'll do an unknown, right? You'll analyze an unknown. So we standardize first, right? So you use solutions that you know what they are, right? And so you take one solution and you make like a serial dilution, and then based upon that, you should be able to do it. Hold on one second. Can I put you guys on hold for a minute? But while I'm doing that, I'm gonna have you guys work on this problem right here. Okay, so I'll put you guys in groups to work on this problem because it's exactly the same concept, right? That we just did, the exact same problem that we just did, where we're balancing out that equation. But you need to first realize what the equation is. And this is phosphoric acid, even though it's a pH, that's an English way of spelling. I apologize. So, and we're neutralizing with sodium hydroxide. Okay? You guys can handle it? You want me to put you in groups? You ready?
Yes,
Okay.
we're ready.
Let's see. 3 groups of 5.
Sure.
Sounds good.
Okay. Good luck.
I need Jessica's stylus. Oh.
You got this. You got this.
Jessica, you know, this looks so bad. Do you want me to write the whole conversion down?
What do you mean by the whole conversion?
Do you just want me to write the answer? Or do you want me to write
No,
the
no,
whole?
you have to go through the steps. I mean, otherwise it defeats the
Okay.
purpose for those who don't
Okay.
know, right? You're the instructor. I'm the student.
Oh gosh, good luck, everybody.
Show us your ways, Jessica.
I am no teacher. That's a 1. That's a 1. Oh. See, it's getting worse as time goes on.
Readable. I was gonna say it's edible. It's readable.
Good. The 5.
taking our protein shake.
Oops, it's the other way. Okay. Fingers crossed.
Let's see. Maybe I'm doing this wrong. Hold on. My calculator wrong. Okay, so where did you get the 2 from?
From the balanced equation.
Okay. Okay. Let's see, divided by. Okay, looks, got your molar. So you want to put the unit still on that side, down here. Looks good so far. Okay, so I have question. Okay, yeah, so you definitely want to show your balance equation. So I know where that's coming from. But yeah, that looks great. Good job. Virtual high five. Okay, it isn't face to the hand, you know, it's a good thing. Okay, so are you guys feeling comfortable with this? You understand how to use this? Okay, So we're gonna stop for chapter 16 here. That's what this is the bulk of it that I want you to get. Now, although I'm just gonna kind of scroll through some stuff real quick. There's another example problem, but this is dealing with equivalencies. You can do the same thing with equivalencies based upon the same thing, since you're also working with a volume, right? And so we can use equivalencies to sit there and get us to the same point. And that's the same thing with using normalities. So we're not gonna focus on that. I wanted you to focus primarily on molarity because that's the one that you're gonna encounter the majority of the time. Okay, so I do want to talk about molality. So molality is used for when we're working with colligative properties such as boiling points, freezing points. So anytime that you're working with boiling points or freezing points, because we're talking about, let's say, like for instance, salt and water, right? So salt is going to be our solute, and then the water is going to be our solvent, right? So you can use the number of moles to sit there. Your molality is going to affect your boiling point or your freezing point. So delta T represents the change in temperature, right? So it would be your delta TF is, what does water normally freeze at? What is the point that water normally freezes at? Anyone? Anybody know?
Is the question?
What temperature does water normally freeze at?
Is it 2.2?
2.2?
Mm,
No, it's not
32
2.2.
degrees.
How many?
32 degrees Fahrenheit.
It's 32 degrees Fahrenheit. How many degrees Celsius?
0.
0 degrees Celsius, yes. So normally water freezes at 0 degrees Celsius, right? Normally, okay? Now, if we put salts in our water, such as sodium chloride, how does that affect our freezing point? Does it increase our freezing point, or does it decrease our freezing point?
decrease.
It decreases, right? So if I have a whole bunch of salt, it's harder for water to freeze. Does that make sense? Okay, so because of that, if we add more and more salt concentration, that's going to affect our freezing point. And so that's what this equation basically says. So it says this delta T means the T of your normal freezing point minus the new freezing point, right? Okay, so the difference between that, say F1, F2. Okay, so this represents your depression in your freezing point. It's that change in temperature of that. Okay, and so there's a constant for each solution that you're working with. There'll be a constant for water. There'll be a constant for, let's say it was alcohol or something like that. So whatever solvent we're working with, there will be a constant for that. And so our delta F, that change in our freezing point, is going to be a function of that constant times the molality. This is molality. Okay. So every solution has a KF, or every solvent, not solution, every solvent has a KF that's associated with it. So if we have pure alcohol, we're going to have a KF associated with it. Let's say we're diluting our alcohol in water, so then we would take the molality of the water over the kilograms of the, or the moles of the water over the kilograms of the alcohol, and then that's going to be our molality, right? And so we would be able to sit there and do a calculation based upon that, okay? So again, we could sit there and use that, the molality and that constant to sit there and calculate that change in temperature. And since we know that one of them in the case of, well, alcohol is different than water, but let's say if it was water, then we would say water, freezing point of water, minus that difference to get the calculation of what we would want. So let me give you an example. It's all kind of fuzzy until you use it. Come on. So clear. Okay, so we have some purple dye. The purple dye is dissolved in water, right? So as the solution freezes, you see how like all the purple dye is starting to get all caught up together? Hello?
Yeah.
You there? Okay. So all it is that water is actually surrounding. And so these guys are starting to get organized around it. So the water is being kind of collecting that purple dye in a certain point. But that purple dye affects how that water is going to freeze, okay? And that's the point of molality. Molality is talking about how your solute is going to be affecting your solvent. And when we talk about those colligative properties, that's the effect of the solute on the solvent, okay? Yeah. So the way that we would determine the freezing point of this guy would be dependent on the solvent. In this case, I mean on the solute. Yeah, come on. Oops, I'm trying to put you guys in rooms again. Here's my conversion factor. Okay. Okay, so your KF for, I had to look it up. So your KF for water Okay, so your KF for water is going to be 1.86, and the units for that is going to be Celsius, kilograms per mole, or you can say Celsius per molal, okay? So that'll be the other way of saying it. Okay, so if we're doing a calculation of the freezing point of a solution of urea, so since we have the grams of urea, this is the chemical formula for urea, right? So how will we change that to moles?
Calculate the molar mass of it.
Okay, so the molar mass of urea is 60.06 grams per mole, right? So then now we got the number of moles. So we multiply this by the number of moles. We have the number of moles of this guy. So then how do we calculate the kilograms of water of this guy?
Convert grams to kilograms.
Convert grams to kilograms, right? So then that's going to give us, so let's go 250 grams of H2O divided by 1,000 grams equals 1 kilogram. So we get 0.250 grams. Kilograms, sorry. Of water. And then we know molality is just moles over water. So we just divide this by that number. So that's what. Okay, so then this would be our molality. Our delta TF, which is just that change in the pressure. Temperature is just our KF times our molality. So then we just plug it into the equation. This is our constant. And if you guys do get this question, your constants will be given to you. But I doubt you're going to have a question like this. If you do, you'll probably just have one, okay? Oops. Okay, so that represents the change in temperature. So in that case, if I say my TF1, which would be 0 degrees, minus my TF2 is going to equal 1.4 degrees Celsius. We know that water normally freezes at 0 degrees. Now we're saying that the change in temperature is, so now water would now with this solution, water would freeze at negative 1.4 degrees. You guys see that? Yes, no, maybe?
Maybe.
Maybe. Okay, so let's do one with salt.
Would we start with the 25 grams?
Okay. So 25 grams. And I should probably let's put some decimals here so we have some significant figures. Okay. So my 25 grams of what?
Sodium chloride.
Okay, what am I going to do with it?
Convert it to moles.
Convert it to moles. So how do I do that? How do I convert to moles?
The molar mass.
Okay, so what is the molar mass of sodium
23.
and chlorine?
It's 35.45.
Okay, so what am I going to do with it now?
The molar mass on the bottom.
Okay, and up top?
1 mole.
Okay, so what does that equal? Okay, and so I got moles of sodium chloride. So what's my next step?
Is it the milliliters of water?
Okay, milliliters of water. So I have 500 mils of water. And what am I going to do with that?
Can we convert that to kgs?
Yes, we would convert that to kgs, but first we'd have to convert it to grams, right?
Right.
And that's what the
So-
density is for. So 1 ml equals how many grams?
1.
Okay. Now, that's an easy conversion. So now how do I convert grams into kg?
It's 1,000 grams per 1 kg.
Okay, so then that's half a kilogram of water. So then what do I do with that?
Plug it in to find the molality.
Okay, so I want to determine the molality, little m. It's going to be equal to moles over kg. So then that's going to equal 0.427. Okay. Oops. Okay, I have 0.854 molal. What do I do with that?
I know that the degrees Celsius goes on top of molality, right?
Does it go on top of? Oh, yeah. So you're saying your delta T F is going to equal your KF, that's your constant, times your molality. Okay, so that's going to equal what?
See, I'm a little lost. Where would we, how would we find the constant?
It's given to you. Constants are mostly given to you, like your density is given to you, right? Or you know it offhand. So your KF is given to you right here. I'm giving it to you. Do you see it?
Oh, I see. Yeah. I had it blocked. Sorry.
Yeah. Okay, so your KF is going to be
1.86.
degrees Celsius over molal. And then we're multiplying that by what? What is that? That little m stand for?
The molarity.
Molality.
Molality. Oh my
Yes.
gosh.
So then that's going to cancel out. We multiply that straight across. So your delta TF is going to equal So if your delta TF is going to equal 1.59 degrees Celsius, so what is going to be your new freezing temperature or your new freezing point? Water freezes at what degrees?
32.
Okay. 32 degrees what?
Celsius.
Not Celsius.
Fahrenheit.
Fahrenheit.
Fahrenheit. So how much does it freeze at Celsius? Because we have these in Celsius. We want to keep the units the same units, right? Otherwise, you're getting yourself in a lot of trouble.
0.
0. So we say TF. Say TF1 is equal to 0. So delta T is going to be TF1 minus TF2. And we're saying that is equal to 1.50. Sorry, 1.59. So if F1 is 0, then can we solve for, if TF1 is 0, can we solve for TF2?
Yeah.
Okay, what is it?
32.
What was that?
$1.59.
So negative 5.9. Negative 0.159.
Yeah.
Piece of cake? Yes, no?
Yeah, just need to do it 50 more times.
Okay, so now this is true for your boiling temperature and your freezing temperature. The only thing difference is that your freezing temperature is going to have a different constant than your boiling temperature. The equation is going to be exactly the same. Instead of saying delta F, you'll say delta B for boiling, right? It's going to equal KB times the molarity. Exactly the same thing. So they're going to be interchangeable. The only thing that's going to be different is the equation. For boiling temperature, your delta KB, the change in boiling temperature, is going to be equal to KB, and that's going to be a constant that's going to be given to you, times the molarity. And then for your freezing temperature, it's going to be delta KF is equal to your constant that's an F times your molarity. Okay? And again, these values are going to be given to you. Usually it's a table. You'll have something for water, or you'll have something for alcohol, or something along those lines, depending on what you're working. Okay? Questions, concerns, Gash? Credit? Okay. So, are we good? Okay, take a picture, because you're going to have at least one question. Everybody got their picture? Okay.
Yeah.
Let's see. Okay, now we're talking about gases. Okay, so let me give you the properties of gases real quick. So one of the properties of gases can be expanded or compressed, right? So that basically means this is what a gas kind of looks like. So you have particles, you have each gas molecule there, right? But it's occupying this whole space. So we can actually compress it to make those gas molecules get closer together. Now we know that gas molecules are just moving really fast and they're occupying the space that they can occupy. Kind of like that dancer on the empty dance floor. You guys seen that one guy that's all by himself, dancing all by himself all over the dance floor. You've seen that before, right?
Yeah.
Yeah, that's usually me, so. Okay, so, but as it gets more and more compact, right? Or you go into a smaller dance floor, that person's gonna have less room. And you're gonna have less, you're gonna still have the same number of people that are dancing, but they're gonna run into each other a little bit more, right? And you've kind of seen that too when they start to drink a little bit. Okay, the same thing happens if you expand it. Like if you expand the gas, the molecules have more room to sit there and move, right? And so they're going to try to occupy as much of that space as possible, okay? And so that's what we mean by compression and expansion. So compression, pushing it in together, closer together, expansion, further apart. You guys know about the different states, right? And you know that here, these guys, air is going to be less dense than water because those molecules are really close together. Where here it's a gas, they're going to be further apart, and so they're going to just try to occupy the space that's available for them to occupy. And then we know a solid is really compact, right? And so gases are going to have low density, right? Because you have less molecules per given space compared to the other guys. We also know that you can actually mix gases, right? And if the gases are inert, meaning that they don't react with each other, they'll stay mixed. But that's also going to change what we call the pressure on it, right? The more gases you put in there, right? They could be different gases. It's going to affect the pressure on the component, right? But it doesn't necessarily mean that they're going to react. And then also, depending on the density of the gas, like how much of those molecules you actually have, I should say the density, but the concentration of the gas, you could, if gases do react, you could affect whether they're going to react effectively or not by having the concentration being really low, right? So the probability of those atoms running into each other or those molecules running into each other are going to be much less if you have a very, very big volume than in the case of if you put something very tight. Like for instance, how many of you guys have been to Disneyland?
Yeah.
Yes.
Yeah.
Happiest
Or
place
Dis-
on earth.
What was that?
Happiest place on earth.
Yes, or Disney World, right? So,
Yes.
okay, so how many of you guys been to like a carnival at, at your local carnival, the one in Kalinga? What is it called? The Horned Toad Carnival or whatever. You guys, don't you have a carnival during the Horned Toad Parade or something like that in Kalinga?
I was supposed
Anybody
to go
from
to rodeo in Fresno, but they canceled.
Yeah.
Okay, so you know how big Disneyland is, right?
Yeah.
Oh yeah.
And you know how big your Fresno Fairground is. So let's say
Yeah.
you were there with friends and you guys all separated and went everywhere. What is the probability of you finding your friend in Fresno compared to the probability of you finding your friend in Disneyland?
I
It
probably
would be a lot.
find them easier in Fresno
It would be a lot
Yeah.
easier in
because
Fresno
I
than it
know
would be.
where everything is.
Yeah.
Well, not only that, the size, right?
Yeah.
Think about
Yeah.
the size.
Population.
Fresno's
It's much-
Fairground compared to
yeah.
Disneyland. Disneyland is huge compared to, here, this is Fresno's Fairground. This is Disneyland, it's like, so
Yeah.
you're going to definitely find them here at some point, but where in Disneyland, you may never see them again, right?
I
So,
hope I do.
so the point is that the probability of you guys running back in together are more in a smaller space than it would be in a larger space. So that's the same thing with gases. So if you put them in a smaller space, probability of them running into each other and forming a reaction is better in a smaller container than it would be in a really large container. Do you understand? See, the baby says yeah. Look at that. Oh, damn it, the baby's the only person that answers. That's ridiculous.
Who doesn't answer?
I said the baby is the only one that answers.
Oh,
What else does?
yeah.
Okay. So when we're talking about gases, gases are going to be acting in all different directions, right? And so you're going to get pressure of your gases is going to be exerted in all uniformly, all the way around, in all directions. Where liquids is only going to be exerting in the part where the liquid is at, right? It's not going to be affecting the stuff above it, above the liquid, right? It's not going to be affecting the pressure is only going to be in that liquid component. Do you understand what I'm saying? So it really just depends on the depth of the liquid. That's the only part of the pressure that you're going to get, where gases are going to affect everything. It's kind of like you blowing a balloon. When you blow up a balloon, what happens? Does only one side blow up and then you get a little kink out, or does the whole thing blow up evenly?
The whole thing.
Okay. So, do you guys remember the kinetic molecular theory? Talked about it. Kinetic means what again?
Moving.
Movement, right? So kinetic means movement. So kinetic molecular theory means movement of molecules, essentially, right? So all we're saying is that gases are going to be moving, constantly moving, right? And so since they're going to be constantly moving, they're going to be constantly moving in that empty space, throughout that empty space, okay? So under ideal conditions, because things are going to be moving, you're going to neglect the fact that they may have charges or attractive forces with each other. Now that's going to be with the ideal gas law, right? There's another part of the law, the non-ideal gas law, which basically will take that into effect, which we want to talk about, right? So, and the other thing is, if I increase the temperature, what do you think is going to happen?
We'll move faster.
It's going to move faster. So just like you, if the ground is hot and you're barefoot, you're going to move faster than you would be if it was, let's say, cool or, normal temperature. The hotter that ground gets, the faster your feet are going to be moving, right? You want to get into that cold space. Okay, so this is just basically telling you that a lot of the area associated with gases are going to be empty space rather than filled with occupied with space, because you're going to have those molecules that are going to be constantly moving, and then you're going to be able to only capture some of them in this. Okay, so pressure is going to be basically the force over the area. So it's the force exerted over a given area, okay? So that's what pressure is going to be equal to, or you could say P equals to FA. And the things that are going to affect your pressure is going to be your volume, it's going to be the amount of gas, the quantity, number of moles, and the temperature, okay? So those are things that are going to affect it. Now, think about it. So if I have my bottle, my water bottle here, right? And I blow air in it, okay? And then I cap it really fast. And then I pump up oxygen in it, right? And I keep it fast. And then I pump more in there. What's going to happen over time?
Would the bottle like explode or something?
The water eventually is going to explode. Why?
Because there's too much pressure that's building up inside of the bottle.
Is the pressure building up inside of the bottle, or is it that I'm adding more and more gas to it?
Adding more gas.
Okay, so I'm adding more gas. Okay, now let's say I have this water bottle, right? half of it's filled with water. I have air in here, and right now it's pretty firm, right? So when I stick it in a microwave, and let's say the plastic won't melt, right? Plastic don't melt, right? Initially it won't, because microwaves basically heat up the water molecules, right? So if this is good plastic, it shouldn't melt. But I have the cap on. What's going to happen?
Water will expand.
Will the water expand?
The vapor.
So you're saying the water is going to become steam, right? And then that's going to excite those water molecules, or the water molecules have been excited by, and so that's going to cause them to move to become steam. That's what you're telling me, right?
Yeah.
Okay. And then you said, somebody said it's going to explode. Why is it going to explode?
Changing temperature.
Because I'm increasing temperature, and as I increase temperature, what's going to happen?
Temperature and pressure, right?
Yeah, so temperature and pressure are going to increase, and they're going to be directly proportional to each other, right? As the temperature increases, the more pressure you're going to get, right? Have you guys ever had a bag of chips and had them in your car, and the bag gets really puffy?
No, they're gone.
That's because you eat them. You're not supposed to eat them. Just leave them in your car. So in the morning, put your bag of chips in the car, right?
Dr. Henry, I never leave my chips in my car. It's gone. There's no such thing as leaving chips in the car without eating them.
See, you're ruining my experiment here, you know?
Okay,
So,
okay.
but you'll notice that if you let them sit, particularly like, don't park your car in a covered area, let it sit directly in the sun. Put them on the windshield.
Yeah.
What's that?
And the heat, and then it expands.
Yeah, that's right. It expands, right? And it expands because the gas molecules are being heated up, and then they're moving faster, and they're just taking up more space because they're just bouncing off anywhere. And that pressure is going to expand directly proportional to the temperature. Okay, so we know that volume is going to affect it. The more you pop in there, the more you push in there, it's going to affect the quantity, and then also the temperature. All three are going to affect pressure, right? So pressure is important, in other words, and we need a way of measuring pressure. One of the ways that we can measure pressure is by using a barometer, right? So this is a mercury barometer. The way a mercury barometer works is that the atmospheric pressure is pushing down on the mercury. The mercury is then being pushed into the cylinder, right? The cylinder has a vacuum, so there's no air in there. So then what happens is it will actually move up this cylinder, and then by measuring the distance that it actually moves up, gives us an idea what the pressure is. And so the first form of barometers were basically measured in what we call millimeters of mercury, because mercury is able to move up this scale in a nice fashion, right? Okay, so 1 atmosphere, and you want to write this down. Atmosphere is basically atmospheric pressure. 1 ATM is equal to 760 millimeters of mercury. So that's how far it would rise. 1 normal atmospheric pressure at sea level is going to rise about that much. Okay? So 1 ATM is equal to 760 millimeters of mercury. Okay, so we can actually establish a relationship between gas pressure and volume, right? So gas pressure and volume are inversely proportional to each other, meaning that as pressure goes up, volume will go down. Okay, So what do I mean by that? So as pressure goes up, my volume is going to decrease. Okay. So as volume goes up, the bigger your volume get, your pressure decreases. Okay. So let's say, for instance, I have this tube here, right? And I have so much gas in here. So this is a 50 mil conical tube. And I take all of this gas that I have in this conical tube and I transfer it to a smaller conical tube, let's say a 5 mil conical tube, which I don't have. Well, we'll use my chapstick. I transfer it to my chapstick. Okay, this volume, which volume is bigger? My chapstick volume or my, can you guys see my screen? Hold on. Let me stop sharing. Okay, can you see it? Conical tube, chapstick. Okay, so if I transfer all of the gas in here to my chapstick, which one is going to have the higher pressure?
The smaller one.
The smaller one, right? So that means that the volume, which one has the bigger volume? The chapstick or the conical tube?
The tube.
Okay, the tube has the bigger volume, right? So if I transfer all of the gas from here to this would have more pressure. So do you understand? Smaller the volume, the bigger your pressure. The bigger the volume, the smaller your pressure, right? Inversely proportional. You guys see that?
Yeah.
Okay. Are you guys tapping out on me already? You can't tap out on me. This is the most important part. This is the home stretch, the last thing that we're talking about. Okay.
Okay.
So
I'll keep going.
What was that?
I'm not tapping out.
That's good. Okay, so the amount, right? So the amount is going to be directly proportional, right? So my conical tube here, so I put in 50 mils of oxygen gas. Okay. Now I put a clamp on here, and then I put in another 50 mils of nitrogen gas. And then I put another 50 mil of hydrogen gas in there. So is my quantity increasing?
Yes.
I have 50 plus 50 plus 50. And I should say 50 mils. Let's say 50 moles. 50 moles of nitrogen gas in here. And then I have 50 moles of hydrogen gas in here. And I have 50 moles of oxygen gas in here, right? Is my quantity increasing?
Yes.
Yep.
Okay. So is my pressure increasing?
Yes.
Yes, right? Does that make sense? The more stuff you try. Okay. How many of you guys have put stuff in your closet? You clean by hiding stuff. Like your boyfriend's coming over or your girlfriend's coming over, right? And you don't want to look all messy and everything. And you shove it in your closet. Anybody do that? Don't
Yeah, I
lie. You
think
know you do.
Even when I was
I know.
younger.
And then you realize that you have this like one little small closet you shove everything in, right? And if you just keep shoving stuff in there, what's going to happen?
It'll overflow or something.
It'll overflow, bust open eventually, right? Because the pressure's got more, right? The more stuff you shove in there, it's going to get more and more pressure, right? Okay, so let me give you another analogy. This is a good one, and I know everybody has done. Well, not everyone. Okay. So you've gotten fatter, right, over COVID.
Oh, heck yeah.
Okay. And don't lie. You know, you don't have to say. We don't have to say about how much. We all got a little. I see it in everybody's face. Everybody got a little
Oh, I
chubbiness
know.
going
I
on.
eat every hour.
Yeah. Okay. So now those pants that used to fit you perfectly, they were perfectly fit, right?
More
Now,
like shorts now.
Okay, now
So
you
they're
have to get on the
stretchy.
ground and put them up, pull them up and you're like, okay,
You gotta jump.
what was
You have
that?
to jump to pull. You have to jump to pull them up.
Yeah, exactly. Exactly. Okay, so that's another example, right?
Oh
So
my gosh.
we've got more, there's more of us now than there was before, right? And that volume is basically staying the same, so it's gonna have more pressure. And you notice how the little button that your pants button, it's about to pop any minute, right? Because all of the pressure, right? So
Use a
that's
rubber
another
band.
example showing you, right? Exactly. Yep. Okay, so those are examples to help us remember that, right? Because that's how we know that, hey, it's directly proportional to pressure. So the amount is directly proportional to pressure. Okay, so I talked to you about atmospheric pressure. So we know that 1 atmosphere is equal to 760 millimeters of mercury. Millimeters, Hg, mercury, right? So a torr is equal to 1 millimeter of mercury, which means that 1 atmosphere is equal to 760 millimeters of mercury, which also means that 1 atmosphere is equal to 1 torr. A Pascal. Pascals are SI units. That's the units that they use up in Europe. And so a Pascal is basically equivalent to 1 Newton per meter squared. Okay, so that's what 1 Pascal is equal to 1 Newton per meter squared, which is also equal to 1 ATM is equal to 101,325 pascals. Okay, which is going to be equal to 101.325 kilopascals. Okay, so a bar is equal to 100,000 pascals or 100 kilopascals. So 1 bar is equal to 1,000 pascals. So now you know that. How many bars? How many bars will equal an ATM? So 1 ATM from our other screen. So 1 ATM, is equal to 1,001,325 units, pascals. Sorry, PA. So how many bars? 1 ATM is going to equal how many bars? How would I calculate that?
Would you divide the 101,325 by 100,000 PAs?
So would you just do dimensional analysis? So we can start with 1 ATM.
Yeah.
We know that 1 ATM is equals to how many pascals? Or kilopascals or?
101,325 pascals.
Okay, so 1 ATM equals 101,325. I'm say 101,325 pascals. How many pascals are equal to a bar?
100,000.
So 1 bar is going to I mean, 1 ATM is going to equal how many bars?
Mm.
1.01325, I think.
That is correct. My pen is running out of ink. Okay, piece of cake. Okay, so 1 ATM is equal to 22.92 inches of mercury. Of course, where do you think they get the inches of mercury? Who do you think uses stuff like that? And what about pounds per square inch? Who uses that? How much pressure do you put in your tire?
It's like
Or
32.
What was that?
So I think my tire is 32 PSI.
32 PSI. So we know we're in the US, right? We have to use inches, and we got to use, so we use pounds per square inch, right? And we also use inches of mercury, right? So that's definitely a US thing, right? So your tires are typically 29 to 32 PSI, somewhere in there. Okay, piece of cake. And so you know how to use this and know how to do the conversions. Now you know what all of them are in terms of ATM. This will be provided to you for your exam. Okay, so the way that we do, another way that we can measure pressure is basically using an open-ended manifold. An open-ended manifold is basically easiest ways for me to show you. So. Okay, so here we have a tube. We have a flask. The flask has the stopper. Now we have what we call this is a U-tube. This U-tube is attached to this gas that's being produced in here in our flask, or that's in our flask. So if the pressure inside the gas is greater than the atmospheric pressure, the mercury that's in this tube is going to be shifted. Okay, and as it shifts, you're going to be able to measure the distance of the mercury from this point to this point. Okay, so that would be your difference in mercury, right? So this represents the pressure that's causing the change in the mercury. So the pressure on the gas is going to be atmospheric pressure plus that change in pressure associated with the gas and the atmosphere, right? So it's going to be the atmospheric pressure and that pHg. Okay, if the pressure of the gas that's in the flask is less than atmospheric pressure, then what's going to happen is that the pressure from the outside is going to be pushing more, causing the mercury to go up in this direction. So that change now is going to be subtracted from atmospheric pressure. So Pg represents the pressure of that gas that's inside of here. The PA represents atmospheric pressure. It's opened up to the atmosphere. The Hg, the pressure of the Hg, is just the change in distance in millimeters of mercury, right? And so that's what we use to calculate the overall pressure that's in the gas. Okay, does that make sense? Have any of you guys opened a bottle of water and squeezed?
Mm-hmm.
And then what happens?
Water comes out.
Water comes out, right? So that's what you're basically doing here. So that squeezes that pressure that's associated with you squeezing. Here, it's just the pressure that's associated with that gas. So you have more pressure in here, so it's going to cause the mercury to start trying to shoot out. You guys see that? Where here, if the pressure on the outside is greater, right, the water just stays there. Okay? Or if the, let's see, best way of saying it. So let's say you have less pressure on the bottle here. Let's say I squeeze the bottle. Oh, how many of you guys have played with the little booger pooker, the booger squirters? How do you suck your kids' boogers
The
out?
booger suction?
Yes, the booger suction, right? So
Yeah.
what do you do? What do you do with that?
You squeeze it and then you put it in their nose.
Okay, and you put it in your nose, and then what happens?
So it sucks the boogers out.
So do you let go a little bit so it sucks it out?
Oh, yeah, yeah.
Okay. So have any of you guys ever played with that? Or what you guys probably do, a pipette, right? You guys have pipettes?
Yeah.
Yeah.
Yeah, which you can also use as a booger sucker too, right? But it's a fine tooth booger sucker. Okay, so what happens? We squeeze that bulb, and then what happens?
Pushes air
Squeeze the
out.
bulb. Okay, pushes the air out, and then when we let go of the bulb, what happens?
Being sucked in.
Things get sucked in, right? So I can suck in water or anything like that. So that's what's happening in this situation. Oops. It's like your atmospheric pressure is greater than here. So then as a result of it, the outside is greater than it. So it's able to get pulled up in there. And so air is being pulled up in here because this pressure is greater than this guy. So it's pushing it in this direction. Okay. Okay, so the pressure, so the pressure inside a steam boiler is 1,427 psi. So express the pressure in ATM. How would I do that?
Would you start off with the 1,427 psi?
Okay. So 1,427 psi. And then?
And then you'd use your equivalency of
Okay. Okay.
Sorry.
What is the equivalency?
of 14.70 psi.
Equals one what?
Atmosphere.
Okay. How many sig figs should I have?
4 sig figs.
Okay.
So would it be 97.07 atmospheres?
That's correct. Piece of cake?
Dr. Henry, please, how did we get 4.7 psi?
How did I get 14.7?
Yeah.
So that was given to us 3 slides ago
Oh, okay.
as a conversion.
Mm-hmm.
Okay, questions, concerns, Cash? Okay. Okay, good. Piece of cake, right? Okay, so now here's a hard question. It says the pressure in an automobile tire is 29 psi on a day. the weather reports states that the barometric pressure is 30.90 inches of mercury. How would you report the absolute pressure in the tire to a colleague? So absolute pressure is a combination of the pressure of the automobile or whatever you're looking at, plus the atmospheric pressure. Okay, don't you guys all yell at me at once.
Should we just start with what we're given
Okay,
first?
so what are we given?
Should we take either the 29 PSI?
Okay. And what do we know about PSI and atmospheres?
There is 14.7 PSI per 1 ATM.
Okay. And then how many, for 1 ATM, how many PSI, I mean, how many pascals or kilopascals is it? We'll say kilopascals.
It is
1 ATM equals how many kilopascals? Well, we know it's 101,325 pascals. So if I just divide that by 1,000, that's going to give me my kilopascals. So I get to say 101.325. So since 1 atmosphere is equal to 14.7 psi, which is also equal to 101.325 kilopascals, can I just do this to save myself some time? Is just put it kilopascals and psi equivalency. Can I do that?
Yeah.
Okay. Oops. Okay. And then what about the barometric pressure?
Would you
So
convert?
Oh, go ahead.
Oh, sorry.
No, go ahead.
Would you convert those into kilopascals too?
That's right. And then what is the conversion? How many ATMs equals inches, millimeters mercury?
760 millimeters of mercury.
Not millimeters. I'm sorry, inches of mercury.
Oh, sorry.
No, it's my fault.
29.92.
Okay, so I can say, do the same thing I did right above. Only thing I use now inches of mercury. Inches of mercury and questions so far?
No.
Okay. And then if it's the total, the absolute pressure, then what do I need to do? Last part.
Add both of them together.
Okay, add them together. So I have 2 sig figs in this case. So about that. And then we have 101, 1, 9. Both of these are kPa. We add it together. What do we get?
Will that be 3.0 times 10 to the 2?
That's right. Because we get okay. So 2 sig figs, right? Because here, but we want to make sure we have our placeholder. So we're going to put it in sig and scientific notation. Piece of cake. Okay, so we're going to stop here. And tomorrow I'm going to have to take one of your lab days away from you to finish this up. So that Wednesday you guys can do your presentation and whatever else you got to do. Okay?
Yep.
So I will see you guys here tomorrow. Mañana.